This is the fourth video in my series on causal inference, and this one is going to elaborate on some of the other causal measures of effect. In the last video, we touched on the average causal effect in the form of a causal risk difference, but in this one we're going to talk about the relative risk and odds ratio and go through some of the causal notation. I've already done videos on some of these measures of effect, but this one is more in the lens of causal inference, basically. So as always, I need to acknowledge this book called What If by Miguel Hernan and James Robbins, as it has basically a lot of the ideas that I'm going to be talking about come from this book, and I need to acknowledge that. As I talked about in the first video, measures of effect are one of the major Bradford Hill criteria for causality. So if we look at these two findings, one saying that dementia was 100 times higher in alcoholics and another saying dementia was 1.2 times higher in alcoholics. Basically, the one on the left is in a way providing a greater evidence for causal inference, as I guess the strength of association tenet of the Bradford Hill criteria is just that stronger associations are generally more likely to be causal. So if I was to make a statement such as those who smoke were at a 10 times greater risk of lung cancer in their lifetime, it's important to know how that 10 times greater, basically where that comes from. I think that's important to understand before we move forward. So it would come from data like this. This is really common in epidemiology, this 2x2 table, where on the left margin we have smokers and non-smokers, and on the top we have lung cancer positive and lung cancer negative, and then we have a distribution of the combinations of those two things. So a relative risk looks at the risk of the outcome in the exposed, so the risk of lung cancer in smokers, and divides that by the risk of lung cancer in non-smokers. So just starting with how that numerator is calculated, the risk of lung cancer in the smokers, you take the number of smokers with lung cancer and divide by the number of smokers in the study. So 100 in that top left corner, the smokers with lung cancer, divided by 1,000, the total smokers, so that far right margin in the smoking row. And then we get 0.1. And then we can do the same with non-smokers, where in this case it would be the number of non-smokers with lung cancer, that's 10, divided by the number of non-smokers, which is also 1,000. So 10 divided by 1,000, we get 0.01. And then the relative risk, we take those two that we just found, risk in smokers divided by risk in non-smokers, and we get a value of 10. So the risk in smokers, that 0.1, is 10 times greater than this baseline risk in non-smokers, which is 0.01. And those aren't real numbers, that's just to kind of illustrate. But yeah, so that is the relative risk, but there's two other ones. There's the risk difference and the odds ratio. So as far as I'm going to be going through calculations that are unfortunately on two separate data sets, but just kind of showing how the conventional framework of how we find these things, risk difference, risk ratio, and odds ratio, I'm going to show how that differs from how we go about it in the potential outcomes framework. So as I just showed you, this is how we conventionally find the risk ratio, just like I did before, where it's 100 divided by 1,000 divided by 10 divided by 1,000, risk in smokers divided by risk in non-smokers. If we're comparing that to how we would go about it in the potential outcomes framework, as I talked about in the other video in the group level causal inference, there's this is this population of 4 individuals where the pale blue part is just looking at what has actually been observed, where the first 2 people got the vaccine and didn't get sick, and the second 2 people didn't get the vaccine and did get sick. That pale blue is the factual observed combination of treatment and outcome, but if we take as a given that there is this unobserved counterfactual situation where individual 1's observed situation is they got treated, they didn't get the outcome, their counterfactual situation is what would have happened if they were not treated. So in this particular situation, when individual 1 wasn't treated in this counterfactual situation, they did get sick. So there's causal inference at the individual level there that the vaccine prevented them from getting sick. if we separate this group and then reorganize the table, so what I did there basically is made it so now this left-hand table has only treated individuals. It's composed of both real and counterfactual data. And on the right, we have the situation where no one is treated, and it's composed of 2 real observations, 3 and 4, and the counterfactual state for the individuals 1 and 2, who in reality were treated, but basically we're using their data from this counterfactual world where they weren't treated to get a complete table. And now we have this overall population where everyone is represented twice. They're represented once for their real treatment state and represented another time for their counterfactual state. So looking at just among those who were treated, the probability of the outcome if everyone had been treated is 1/4, because you can see that individual 4 got the outcome, but no one else did. So that's a quarter of the people got the outcome in this situation where everyone's treated. In the situation where no one is treated, we can see that 3 people got the outcome, 1, 3, and 4, but individual 2 did not. So 3/4 people get the outcome when no one is treated. So now looking at this conventional framework on the left and the potential outcomes framework on the right, again, like they're 2 different data sets. The one on the left has 1,000 smokers and 1,000 non-smokers. That's a population of 2,000 people. The one on the right is just a population of 4 people. And although it's different data, I think it's helpful to just show how the 2 frameworks go about calculating these measures of effect. So as I alluded to, the main difference in the conventional framework versus the potential outcomes framework is that in the conventional one, it's using only observed data, while in the potential outcomes framework, it's using both observed data, the pale blue, but also unobserved or counterfactual data, which is the pale orange. Another major difference is in the conventional framework, everyone's showing up once, and in the potential outcomes framework, everyone shows up twice. Everyone occurs once in the treated group and once in the untreated group, and only one of those 2 observations is observed. The other is hypothetical, but assumed to be a fixed constant state. So how we go about it, calculating the relative risk, is the same as I showed you before, that 100 over 1,000 divided by 10 over 1,000. But how we would find the causal relative risk in the potential outcomes framework is we figure out, as we did before, the probability of the outcome had everyone been treated divided by the probability of the outcome had no one been treated. And everyone is occurring in both the numerator and the denominator here. So as we found before, we have 1/4 divided by 3/4, and we get an average causal risk ratio of 1/3. And that is assumed to be like a perfectly basically perfectly valid in the sense that, like I said before, everyone is represented in both the treated and untreated group. And what that does is just balance every individual level confounder because they're occurring in both groups. So it's essentially like being matched to yourself. So the risk difference is the next big one. I talked about it in the last video. So the average causal risk difference is the risk had everyone been treated minus the risk had no one been treated. And yeah, that's the notation there, where this y subscript a equals 1 is just the outcome had everyone been treated, and basically the probability of that of the outcome had everyone been treated subtracting the probability of the outcome had no one been treated. Sorry, it's just saying a lot of the same thing. But yeah, and in this case, before with the causal risk ratio, it's a ratio, so the null value is 1. That would mean there's no effect when the value is 1. But now because it's on an absolute scale, there's no effect when it's equal to 0. So how the conventional and the potential outcomes framework would go about this, the conventional one would find the risk in smokers and subtract the risk in non-smokers, considering that to be like the baseline risk. So that would be 100 divided by 1,000. That's that risk in the smokers. Subtracting 10 divided by 1,000, that baseline risk in the non-smokers. And you get a value of 0.09. So when you're a smoker, your risk is raised by 9% above the baseline. So the average causal risk difference goes about it similarly, except again, everyone is represented twice. So in this world where everyone is treated, so that left table, the all treated table, the probability of the outcome is 1 over 4. You can see that individual 4 got the outcome and there was 3 non-outcomes. And in the all untreated table, the one on the right, we can see that individuals 1, 3, and 4 got the outcome. So that's 3 out of the 4 that are in the population. And we get -1 over 2, just like we did in the last video. So the last one I'm going to talk about is the odds ratio, and that one is the most controversial. It's the one that is typically available when the disease is, or the outcome is common, and you're using logistic regression. You're often stuck with that. But yeah, the odds ratio has some problems that I'm going to get to at the end, but in the interest of being a complete video on measures of effect, I'm going to talk about the causal odds ratio. So the notation here gets a bit more complicated now, where in the numerator we have the probability of the outcome had everyone being treated divided by the probability of the non-outcome. So that's what an odds is, the probability of something happening divided by the probability of it not happening. So in the numerator, like I said, we have the probability of the outcome had everyone being treated divided by the probability of the non-outcome had everyone being treated. And in the denominator, we have the exact same odds, except it's among this world where no one was treated. And again, it's a ratio, so the null is when it's equal to 1. So comparing how the conventional framework and potential outcomes framework would go about this, the conventional one is now just looking at the odds in the smokers. So that 1,000 at the far right margin is no longer in play the way it was with the relative risk and the risk difference. Now it's an odd, so it's 100 divided by 900. And then in the denominator, we have the non-smokers, so we have 10 divided by 990. And that comes to an odds ratio of 11. And the way we go about it in the potential outcomes framework, again, similarly, we figure out, so I guess the numerator of the numerator there, we have the probability of the outcome had everyone being treated. So we're looking at that left table, the all treated group, that's 1 over 4. And then the probability of the outcome not happening, again, still looking at that all treated table, we can see that the outcome didn't happen in 3 of the 4 people, so that's 3 over 4. And now in the denominator, we have the probability of the outcome had no one been treated. So we can see on the right, all untreated table, we have 3 people who got the outcome out of the 4, so that's 3 over 4. And then the denominator of the denominator there is the probability of the non-outcome had no one been treated. So you can see that one individual 2 there, didn't get the outcome. And that's 1 out of 4, didn't get the outcome. So it's a little convoluted, but we end up with an average causal odds ratio of 0.11, and that's just a coincidence that the other one was 11. So now deciding whether you're going to use a ratio one, like the odds ratio or the relative risk, or a absolute difference, like a risk difference, there's a few things we need to consider. So they're basically representing completely different things. So a ratio is looking at how many times greater the risk or odds is in the exposed, while the risk difference is an absolute increase in risk from being exposed. And just to show how the two can basically, like, there's certain situations, like when the disease is incredibly rare, that if you use an odds ratio, something might look like it's like 50 times more likely to get the outcome if you were exposed. But if it's already a super rare thing to occur, then increasing the likelihood of it happening by a lot isn't really a big deal. Like, that'll make sense with the example. So now we have this new set of data. We can see that disease is incredibly rare. So like both in this exposed and unexposed group, we have 1,000 people. But in the exposed group, 2 people got the outcome, and in the unexposed group, 1 did. So it's incredibly rare. But if we do a relative risk, we can see that you're twice as likely to get the outcome if you're exposed, 2 people compared to 1 person. But since it is so rare to begin with, when we do a risk difference, so the risk in the exposed, 2 divided by 1,000, minus the risk in the unexposed, 1 over 1,000, we see that it's on an absolute scale, it's a 1% increase in risk. Like the risk has doubled. It's gone from a 1% risk, a 0.1% risk to a 0.2% risk. But doubles sounds way more intense than what it actually is, which is a very, very marginal increase in risk. So you can see that, like, depending on the situation, it might be it might be more reflective of the actual impact of what you're going to do. Like how meaningful is this intervention when it affects no one? It's going to have a big effect. It's going to double your risk, or if we get rid of it, it's going to lower your risk 2 times. So basically, that sounds great, but if it's already super rare, then what you're doubling is already like an insignificant threat to public health, pretty much. Another thing to consider is collapsibility. A lot of people don't like the odds ratio and look for situations where the odds ratio approximates the relative risk. And one of the main reasons for this is something called collapsibility. So just to show what that looks like, we have this collapsed 2 by 2 where we have the exposure positive and disease positive group. Exposure positive and exposure negative. We find the relative risk in this group, 180 divided by 300 divided by 55 divided by 300. We get 3.3. And if we separate this table into, those who consume a high-fat diet and those who consume a low-fat diet, if we break this table, you'll see that this high-fat and low-fat table, if we combined the E positive, D positive cell in both, we'd get 180 there on the left. So it would collapse into that table on the left. We've stratified it now by high or low fat diet. So if we find the relative risk within those 2 strata, the first one we'd have 100 divided by 150 divided by 25 divided by 150. That comes out to 4. And doing the same thing with the low fat diet, it comes out to 2.6. Now, if we take an average of that, here we have 300 people in the high-fat group and 300 people in the low-fat group. So we don't need to do a weighted average. We can just do 4 plus 2.6 divided by 2, and we get 3.3. And that's the same as we got in this collapsed table. So what this illustrates is that when you use a collapsible measure of effect, something like a relative risk, then basically your population level collapsed table is just a weighted average of the 2 strata. And in this case, it doesn't need to be weighted because the same number of people are in the high fat and low fat strata. But when something is collapsible, that essentially means that the true collapsed value, 3.3, is within the bounds of the 2 stratified tables. So 3.3 is between 4 and 2.6. And it is a weighted average of 4 and 2.6. That's not the case with the odds ratio, which I'll show where if we find the odds ratio now, this 300 in the exposure positive and negative group is not relevant because we're doing an odds. It's just 180 divided by 120 divided by 55 divided by 245. That comes out to 6.7. And if we again stratify this table by high fat and low fat and then do the odds ratio for each table, the high-fat odds ratio comes out to 10, and the low-fat odds ratio comes out to 4.6. And taking an average of that, 10 plus 4.6 divided by 2, it comes out to 7.3, which is different than the collapsed odds ratio, which was 6.7. So what that basically means is with the odds ratio, this collapsed population level measure of effect, this collapsed odds ratio, isn't necessarily a weighted average of the stratum's specific odds ratio, and sometimes it can even lie outside of the bounds of 10 and 4.6. So here it's like 6.7 is still between 4.6 and 10, but that doesn't necessarily need to be the case with the odds ratio. It can even be outside of that. So whenever you hear someone talk about non-collapsibility of the odds ratio, this is part of what they mean, and this is what makes it less informative about what's happening in the collapse table because, we can't make these assumptions that the collapse odds ratio is going to lie within the bounds of the stratum-specific ones, or that we can even use the stratum-specific ones to find the collapse one. So yeah, it's a less respected measure of effect, and when you can, you should probably use the relative risk. Another difference is you'll notice we use the same data to find an odds ratio and a relative risk, and the odds ratio one was further from 1. 6.7 is further from 1 than 3.3. So that leads to this kind of general statement about odds ratios that they're generally further from the null and less conservative.